Hey guys, welcome to another A-level maths revision video. So it's been a while. In this video we're going to cover exponential modelling. It's a pretty brief kind of topic, just falls under the exponentials topic overall. But hopefully we shouldn't find this too tricky. So let's jump straight into these questions and see what we've got. So this first question here, like all the rest, taken from previous exam papers. So this question here, with it being modelling, usually the context is pretty much always the same. It's either something to do with animals on an island and modelling the population, or it's usually something to do with temperature of an item. So in this one here, we're looking at the population of the number of rabbits on an island. So we're told the number of rabbits t years after they were introduced is modelled by the equation. So the equation is given here. So 80e to the 1 over 5t. So t over 5 here is our power. Okay. And then t is any positive real number. Okay, so the first question here, part A, asks us to write down the number of rabbits that are introduced to the island. So if the rabbits are introduced to the island, we can tell by the beginning of the question here, it's t years after they're introduced. But if they're introduced, that would mean it's 0 years. It's when they first get there, right? So for part A, what we know here is that t is equal to 0. Okay, and it's only one mark, so we shouldn't really expect any kind of like real calculations here, any kind of tricks or anything. It's going to be pretty straightforward. And the reason for that is because t is equal to 0. So all we do is we substitute t equals 0 into here. So p is equal to 80e. So 1 over 5 times 0, so that's just going to be 0. So this is 80e to the 0. Now, anything to the power of 0, we should know is just 1. So what I get here is 80 times 1, which is equal to 80. Okay, so the number of rabbits that are introduced to the island is 80, so 80 rabbits. So that's just our first mark there. Now, we've only done one. I'm going to clear the working straight away because part B is a little long. Surprisingly for the kind of the 2 marks that it really is. So we start it up here. We should hopefully get through it pretty quick though. So what we're looking for here is the number of years it takes for the rabbits to first exceed 1,000. So we're looking for when the population first exceeds 1,000. So what I'm looking for here is p larger than 1,000. Okay. Well, what we know is that p is equal to this equation here. So I'm just going to set up my inequality like this. So that's 80 to the t over 5, or a fifth t. And this is larger than 1,000. Okay, so all we're doing is we're translating the problem here in words to a mathematical expression that we can go on to now solve. So this here now, we're just going to look to solve this inequality. Pretty straightforward. So first, what we're looking to do here is find the time. Okay, we're looking for the number of years. So we need to solve here for t. So solve for t. So the first thing I can do is divide by the 80 here on this side of the inequality, and we'll also do that on this side. So I get e to the 1/5 t is larger than 1,000 over 80. If you do that on your calculator, that's 12.5. So 12.5. Okay, we're nearly there now. The only thing I need to just consider here now is how do we get this t on its own, rather than it being a power here with the base e. How do we get t on its own? Well, we're going to anti-log here. Okay, so we anti-log, and using the power rule here, we can bring this down to the front. So this is a fifth t, so 1 over 5t, and this is larger. So we've raised everything here with the base of the natural logarithm, so that's ln. This side will be ln 12.5. And whatever you do to one side of an equation, or an inequality here in this case, do it to the other as well. So at this stage now, we're nearly done. Remember, we just want the value for t. So this is t over 5. So to get the value for t, I'm just going to times both sides by 5. Okay, so t must be larger than 5 lots of the natural logarithm of 12.5. Okay, if you put this into your calculator, this is approximately 12.628, so on and so on. So in that case, t, well, the actual value for t, the number of years, must be the next closest value to this 12.628, so that would be 13 years. Okay, so quite a long time for our final answer. Obviously, if this was 12.2, for example, you wouldn't round it down. It would still be 13 years because we're part way through the 12th year. So it will always round up in that sense. Okay, so that's part B. Part C then, not really anything to do with kind of modelling, just a pretty standard differentiation question. We want to find dp by dt. So this is the rate of the pre-population with regards to time here. Well, this is really easy to differentiate. If p is equal to 8e to the 1 over 5t, what we do first is we look at the 1 over 5t and what the derivative of that would be with respect to t. So that would just be a fifth. So what we do is we take that a fifth down to the front with the 80, and we're going to do 80 times a fifth. So that'd be 16. So my actual expression now is just going to be 16 and then the original e to the 1 over 5t. Okay, so that's going to be 16 e to the 1 over 5t there. Okay, so nice and easy there for 2 marks. So that's for part C. And then part D, so if we just line off all our separate questions here. So part D, we want to find p when, so the differential, what we've just worked out, is equal to 50. So straight away we can set this equal to 50. So this is equal to 50. And what we're going to do here essentially is solve this exponential equation for t, and then we're just going to substitute that t value back into our original p, okay, to model the population. So straight away divide both sides by 16, similar to what we did here, okay, with these 2 lines of working. So it's just what we're doing here now. So that's e to the 1 over 5t is equal to 50 over 16. I'm just going to keep it exact this time round, just to make life a bit easier. Again, just like we did here, we're going to bring this 1 over 5t down. So I get 1 over 5t is equal to the natural logarithm of 50 over 16. 50 over 16. And then at this stage here, we just times this through by 5. Okay. So t is equal to 5 ln 50 over 16. Okay. And now all we do is we substitute this t value back into p. So sub into p. So all I'm going to do then is work out p as being 80 e to the 1 over 5 t, where this is t, this is 5 ln 50 over 16. Okay, kind of run out of room just at the very end there, but hopefully you can still make it out. So if I do 1 over 5 times the natural logarithm, this will just give me the natural logarithm of 50 over 16. Okay, so the 1/5 and the 5 will just multiply to give me 1. This is 8e to the ln 50 over 16. And then just using the laws of logarithms here and exponentials, if you've got e to ln of x, that's just simply going to give me x. Okay, now obviously in this case it will just give me the 50 over 16. So p is just simply 80 times 50 over 16. Okay, and if you plug that into your calculator, p is equal to 250. So 250 rabbits there. Okay, and that's it. Question done there. Okay, so that's our first question. Hopefully not too bad. Quite a lot of marks for that really. But that's our first introduction there. So let's take a look at another question. This one's a bit shorter, and hopefully a bit easier. So we've got the area of a bacterial culture growing in milk T hours after midday. Okay, so the equation that models that is given as A equals 20e to the 1.5t, and t is just a positive number here. So the area of the culture at midday, again, just 1 mark. You'll get used to these kind of questions, and what you will usually expect is that the very first question, normally always, you just sub in t equals 0 in. And that's the case here. This is t hours after midday. So if we want the culture at midday, that's just going to be 0 hours. So t equals 0. So we're just going to sub that into here. So a is equal 20e to the 0, which again is just 20 times 1, which is just 20. Okay, so that's the area there. Let's put our units down. So it's millimeters squared. So 20 millimeters squared there. And then for part B, we need to find the time at which the area of the culture is twice its area at midday, giving the answer to the nearest minute. So I think at first it takes maybe a double take just to actually understand what this question is wanting. So what we're looking for here is the time for which the culture is twice its area at midday. So if we've got the area at midday, we need to double that, because that's what we're looking for, the time at which that occurs. So we've worked out the area at midday is 20 millimeters squared. So the area we require is A equals 5. So require A equals 5. So all I'm going to do now is use the equation that we've got and make it equal to 5. So that's going to be 20e to the 1.5t is equal to 40. Again, nice and easy. Divide through by the 20. So that gives me e to the 1.5t is equal to 2. 40 over 20 just gives me 2. And then at this stage here, we're just going to solve this exponential equation. So if I've got e to the 1.5t, we can bring this down to the front, and we're going to antilog here. Okay, so antilog, that's going to give me 1.5t, and that's going to be equal to the natural logarithm of 2. And now at this stage here, we're pretty much done. We're looking to solve for t, so I need to go to this 1.5. So to do that, we're going to divide by 1.5. So ln 2, natural logarithm of 2 divided by 1.5. So plug this into your calculator, and what this gives us is 0.462. Okay. Now remember, t is in hours, so t in hours. But the question asks us for the answer to the nearest minute. So what we know is that this time is 0.462 hours. So what I'm going to do then to put that in minutes is times that value by 60. So in minutes, that's going to be 0.462 times 60. Plug that into my calculator, and I get 27.72 there. Okay, but remember the question asks you to write this to the nearest minute, so this would round up then to 28 minutes. Okay, so after 28 minutes, the area of the culture is twice the area midday. Okay, so that's question 2 done there. So let's move on to the final question here then with exponential modelling. Again, another pretty standard question, looking at temperature. So question 4. And again, we should be pretty used to this by now. We want to find the initial temperature here. 1 mark, again, we're just going to sub t equals 0. Now be very careful, usually it's just kind of one expression. So if you plug, for example, if that 25 went there, the answer would just be 400. But be very, very careful. It's going to be 400 plus a 25. So let's just write it in full. So t equals 0. So all we then do is sub that in. So t is equal to 400 e to the 0 plus the 25. Okay, so what I've got here is 400 plus 25, giving me the temperature. It's 425 degrees Celsius, so quite hot. Part B, we want to find the value of t for which t equals 300, giving our answer to 3 significant figures. So let's do that up here. So we're looking for when t equals 300. So if this is t, this is t up here, all the way across here. What I'm going to do is I'm just going to set that equal to 300. So that's going to look like this. So it's going to be 400 e to the minus 0.05 t plus 25 is equal to 300. And what we're going to do now is solve this for t. So the first thing I'm going to do is get rid of this 25 here. We don't want that on this side. So I subtract 25 off both sides. So I get 400 e to the minus 0.05t is equal to 300 minus 25. So that's 275. And now at this stage here, I'm going to divide both sides of the equation by 400. We want to solve here for t. Okay, so we need to get this as e to the minus 0.05t. So that gives me e to the minus 0.05t. And this is 275 divided by 400, which would simplify to 11 over 16. And then at this stage now, again, we should be getting pretty used to this. We're just solving for t here. So we're going to anti-log. We're going to bring this down to the front. This would be minus 0.05t. If we just close this off so we don't get confused. And this is equal to natural logarithm of 11 over 16. I'm going to divide now by this minus 0.05 because we just want t. So if I do ln of 11 over 16 divided by minus 0.05, what I get here is 7.4938 there. Okay, but we want it to three significant figures, so if we just do that correctly, so we don't lose the mark, that will be 7.49 to three significant figures. Okay, so that's part B there. Now we're best clearing all this for part C. So if we can do that, let's have a go at part C. So again, I'm going to do it at the top here, just so we hopefully don't run out of room, but I don't think it will take that. Now, the question doesn't tell you explicitly what to do. You kind of got to figure that out yourself by the language they use. So they say find the rate at which the temperature of the ball is decreasing at the instant when t equals 50. So the big clue here is one word that they use in particular, and it's this word here, the rate. Okay, when you see that, when you see the word rate, straight away be thinking differentiation, so dy by dx. Obviously my variables will be different for this, but differentiate, okay? Rate of change is associated with differentiation. So I know I need to differentiate here. So what I'm going to differentiate is the temperature, capital T, with respect to time. Okay, so require d capital T by d little t there. So the temperature with respect to time. So all I'm going to do then is simply differentiate capital T with respect to little t. Well, just like we did before, we need to work out the differential of minus 0.05t. So that would just be minus 0.05, and we times that by 400. So 400 times minus 0.05, that will give us minus 20. Okay, so that's minus 20. So all I'm going to do now is just write that out, because that's literally all we do. It's just going to be minus 20, and then our e just goes back where it was with the same power. Okay, so that's the differential there, but we need to work out the temperature of what it's decreasing by when t equals 50. So when t equals 50, sub that into here, that's minus 20 e to minus 0.05 times 50, and if you plug that in, the decrease of 1.64 degrees Celsius per minute. Okay, so that's part C there. And then finally part D, 1 mark, so not loads of work, but it's not particularly easy to see why the temperature of the ball can never fall to 20 degrees Celsius. The way to understand this is we need to understand how the behaviour of this exponential works. So what happens to e to the minus 0.05t as t tends to infinity? So as t tends to infinity, what would happen here? Well, this is going to be a very, very large negative number. And you can try this on your calculator. If you try this on your calculator, what you're going to get basically is 0 here. So as this So as t tends to infinity, this part here tends to 0. So in that case, e to minus 0.05t tends to 0. Okay. So what I get left with then is t is equal basically to 0 plus 25. Okay. Well, in that case, t, the smallest value t can possibly be here, it's going to be this 25. Okay. So obviously it can't go lower than this temperature here. So in that case, it can't fall to 20. So therefore, can't fall to 20 degrees Celsius. And there we go. Okay, so that brings us to the end of this video. I hope this has helped. Any mistakes that you spot, all that good stuff. Like always, just leave a comment down below. Cheers.